welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about physical science. And today, we're learning about bonds, reactions, and solutions. All right, so to start with, I'm going to read you a story. Where did I put my story? Here it is. It's a science story. Okay, this is the book. Anybody ever read it before? You have to pay close attention to get the chemistry out of it. Oh, I've got 5 people in my family, and there's not a one of them I'd swap. There's a sister and 2 brothers, a mother, and a pop.
Wait, you made this book?
That's me. No, this is by Sesame Street. You might have heard of it.
Sesame Street.
5 is such a lovely number. I'm awfully glad I have 5 people in my family. 1, 2, 3, 4, 5. And here's a little foreshadowing of the coming conflict. Well, I've got 5 monsters in my family. A furry wife and scary husband, fuzzy daughters, hairy son. 5 is such a scary number. Oh, I'm so glad I have 5 monsters in my family. 1, 2, 3, 4, 5. Here's the climax. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And here's the denouement. Remember that from literature class? 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Now here are the review questions if you're learning to count, but you're not. You're learning chemistry. All right, so here I've got 2 families, and they are similar to families on the periodic table. So here I've got Muppets, and here I have monsters. How can you tell the Muppets are all in the same family? What characteristics do they have in common?
They have
Their eyes. If you look at their eyes, the pupils are in the center of their eyes and they're looking the same way. Notice the monsters, their eyes don't go in the same direction and they're not symmetrical. They have googly eyes. How else can you tell that the monsters are all in the same family?
Because they all have googly eyes.
They all have googly eyes, but what else do they have in common? What about their skin?
They're more colorful.
Well, they're colorful too.
They look like Emma.
They're hairy.
They're hairy. You can also notice their mouths have a similar shape. Do you see that? And notice also that the Muppets, their mouths have similar shapes. Now, they both have fathers in these families. How can you tell that the ones I'm pointing to are the fathers?
Because they're the only grown male there.
How can you tell? What are you observing?
They're tall.
They're the biggest. They're the biggest in their family. What else do the fathers have in common?
Mustaches.
They both have more hair, like in that area a little bit. That's sort of coming out, looks a little like a mustache. But look at their eyebrows. They have the most eyebrows of anybody in their family. What about their noses?
Their noses?
They're the biggest in their family. They're both purple.
Yeah.
So they have a lot in common. Also look at the youngest members of the family. What color are they both?
Pink.
They're both pink. And they're both the smallest, aren't they? Okay, so now, what does this have to do with chemistry? It's a chemistry idea that has to do with something called periodicity. That sounds fancy, doesn't it? It's considered a hard concept in chemistry, but really it's not. Okay, so on the periodic table, you have families. These that go up and down are called families. Oh, I forgot one question I had to ask you. Do you think the fathers are more like each other or more like their family? They're more like their family. Even though they're like each other a little bit, they have more in common with their family. Notice the mothers both have red curly hair. They're both the second biggest, okay? So on the periodic table, you have families that go up and down. The columns are called the families, they go up and down. The elements have a lot in common with their family. They chemically react the same way as their family. However, they also have representative members. If you look over at that periodic table that tells the state of matter, you see that for a lot of the families, the smallest one up top is so small it's a gas. Hydrogen, nitrogen, oxygen, fluorine, helium, all gases. Look at the bottom of the families. For the bottom of the families, so many of them are so big, they're radioactive. You can tell they're radioactive because the atomic mass is in parentheses. Notice how at the end of every family, the mass is in parentheses. Do you see that? You see that? Okay, so that's the idea of periodicity. The families have a lot in common. Yes, they have representative members, but they have a lot in common. Jaylin, you're in the back row now. Off you go.
Oh my God, who's back here?
You're talking to Ramaya. You're paying attention to her, not me. I know. She's a lot to pay attention to, but off you go to the back. Back to your seat, please.
Jalen, Eddie.
What'd I do?
I just told you what you did. Go back to your seat. Yes,
I
ma'am.
wasn't even talking.
Yes, ma'am.
What do you mean? Yes.
That means you need to go without arguing. Off you go.
I wasn't talking though.
Yes, ma'am. Go back. Don't argue. Just go back.
Saying yes, ma'am.
Because that's what I want you to say to me is yes, ma'am. I want you to just go back to your seat and say yes, ma'am. Just do it. Hurry. Off you go. Okay. So we're looking at, we have a lot to do today. I don't have time for y'all to have conversations going on the side. I just don't have time. So go back to your seat. Okay. So more about the periodic table. The book was called People in My Family. People in My Family.
People in my family.
That's what we just read. And the point of it was that columns, families are more like each other than the periods, rows that have similar members. Now, so if you understand this is considered a hard idea in chemistry, but if you just follow along with this illustration, it'll make sense to you, okay? So what do all the elements want? If you understand this, you're going to understand how they react and why they react. They want to feel like a noble gas. And if you remember, the noble gases is this family right over here on the side, the helium family. Okay, and they want to feel like a noble gas, and noble gases have 8 electrons in their valence level. So that's called having an octet. All of them, of course, except helium, which only has 2 because it's so little. Now, if all the elements want to feel like a noble gas, then you can remember all the elements want if you think of their electrons like children. We're going to say their electrons are like children. Yes?
Are you supposed to put electrons by noble?
Oh, no. They want to feel like a noble gas. Good job. Everybody wants to feel like a noble gas. So they want to have 8 electrons in their valence level. That causes them to be nice and stable. Now, but everybody wants to be like noble gases. So we're going to think about their valence electrons like children. Alkali metals and alkali earth metals are these first 2 columns right here, over here. And they have 1 more electron in this family than noble gases. So like neon's got 10. If you go down to sodium, it's got 11. So it wants to lose its extra electrons. If you go over to magnesium, it has 2 extra electrons, and it wants to lose 2. If it loses 2, it won't be a noble gas, but it will feel like a noble gas because it will have 8 electrons in its valence level. Does that make sense? Okay, so the alkali metals and alkali earth metals want to lose electrons. Now remember we said it was like children is how we're going to remember it. So there are people who don't want their children. They have a baby and they don't want it, and they can take it to the fire department, and there's a little box, and you can put your baby in it, and they won't send you to jail for putting your baby in the box. It's the you can leave a baby for free box. And it's got a little alarm. So people used to have babies they didn't want and they'd throw them in the trash can. They'd put them on the shelf at Walmart. People would be at Walmart looking, for beans, and boom, there's a baby. That used to happen. And then they started making it where the fire departments would lose the baby. So that's where they'd get them. All right, and then they'll put them up for adoption. All right, so which I think is good because I think the adopted parents are probably better than the ones who put them in the box. Okay, so that's who these parents are. These are bad parents who put their babies in the box at the fire station. This family puts 1 baby in. Guess what these do? 2 babies. They're going to put 2 babies in the box at the fire station because they want to get rid of 2 of their electron babies. Okay. The ones near the noble gases, 1 away from the noble gases, they just want 1 more. If they could get 1 more, they're gravy. They feel like a noble gas. So these are the crazy people who steal a baby. It used to be a real big problem. Women would dress up like a nurse, go to the hospital and steal one out of the nursery. Now they have little things on them that if the baby is taken past the maternity area, the hospital goes in lockdown. All the doors swing shut and lock. And they don't try to steal them so much anymore from the hospital. So the ones near the noble gases, like the halogen, want to gain electrons. Now, the nonmetals so like this family, they want to steal 1 electron. This one, they want to steal 2. This one, they want to steal 3. These over here, the carbon family, they're too far away. 4 is just way too many to steal. So these aren't the crazy parents or the bad parents. These are the divorced parents, okay? So nonmetals in the carbon family, they work out sharing agreements. So these are divorced parents. Some of y'all are the little electron in the divorced family that gets shared. Do you get shared between your mom and dad?
My parents got divorced.
Yes, and so that happens sometimes. And they share the child. You get a custody arrangement. So these are our divorced parents. So the ones who want to gain, that's our crazy nurse. The ones who share, those are divorced parents. And I don't have they all want 8. That's our octopus. Okay, so now what are the metals? The metals are here in the middle. What do? They're hippies. Y'all know what a hippie is from the 60s? Hippies lived wild and free. They're hippies. And they let their electrons run wild and free. So in the 60s, yes?
My grandma was a hippie.
My aunt was. In the 60s and in the 70s, early 70s, they had hippie communes. And they would they did not follow sexual norms as far as having partners. Everybody shared. So the ladies didn't know who really the daddy was. So they would just let these kids run wild and free. They call all the women mom. They call all the men dad. And it was an ideal that this was the very best way to raise children. And so you'd see them in documentaries and stuff, and there'd be these little children running around with long stringy hair, barefoot, dirty, and the hippies really felt like that was the best way to raise a child. And you heard it in the song lyrics. There was a song called In Seattle, Growing Up Like a Child, Beautiful, Free, and Wild. The song Born Free, Free as the Wind Blows. All these songs that they thought the best way to live was with no rules, which you can kind of tell by their arrangements. Well, so our metals are like that. They let their electrons just run around free. They don't assign them to any particular nucleus. They're allowed to flow wherever they want, so they're good conductors of heat and electricity, and they're shiny. Now, the hippie communes aren't around anymore. Anybody know why? What was the death of the hippie commune? It was Charles Manson. Have you heard of him? He was the head of one of these hippie communes, and they lived just like that, how I described. But he was also crazy and evil and racist, and he wanted to start a race war so that there was chaos and there'd be a new world order kind of thing. So he got his hippies to go murder people and make it look like it was racially motivated when it wasn't. Everybody involved were Caucasian, the murderers and the murderees. But it horrified the nation. Everybody thought the hippies was just peace-loving, laid back, harmless, and then they're off murdering people. So that was sort of the end of the hippie commune. Charles Manson, helter-skelter, murders, all that. There's lots of documentaries about it on YouTube. Okay, so bonds. So now we not talk about how the atoms become ions. Now we're going to talk about how do they get together and become compounds? How do they form a bond? So there's 2 kinds, ionic and covalent. And in ionic, electrons are transferred. Ionic bonds transfer electron, and in covalent, they share electrons. Compounds must be neutral. That means if one is positive and one is negative, the numbers have to cancel out, so the answer is 0. So in the math, we're going to do this unit. The answer is always 0. That looks easy. So let's talk a little bit more about ionic bonds. What hold them together is that opposites do what? Attract or repel?
They repel.
They attract. Opposites attract. There's an old Paula Abdul song about opposites attracting. I used to show it, but I'm not allowed to show the video anymore because in it there is an animated wolf who smokes. We can't have any representation of smoking in the classroom.
It's a wolf.
It's a cartoon wolf.
That's stupid. It's
But
a
that's
wolf.
the rule. Okay, so on our periodic table, everybody look over there. Do you see those nice little kitty cats? Look how positive and wonderful they look. Elements on that side of the periodic table are metals over here, and they are positive. When they become an ion, they are positive because they lose electrons, and electrons are negative. Did you follow that? So just remember that the ones over there are positive, and they're called cations. So just think about how sweet and positive kitty cats are. On the other side of the periodic table, we have a mean fire ant who is extremely negative. The elements on that side of the periodic table form ions that are negative, and they're not called antions, they're called anions, and they're negative. So ionic bonds are between a metal and a nonmetal, a positive and a negative, opposites attract, and they stick together. That good? Can you follow that? It's our last unit, but it's a little bit hard. Okay, so for example, lithium is in the first column. It wants to lose one electron, and it does, and it becomes Li positive. Now, it's really plus 1, but you know how in math you don't write ones? You don't write 1x, you just write x. We do the same thing in chemistry. We don't write ones. Magnesium is in this family, so it wants to lose 2 electrons, so it becomes magnesium plus 2. Aluminum, right over here, guess what? He wants to lose 3 electrons, so he becomes Al plus 3. Fluorine is 1 away from noble gases, so it steals 1 electron. Electrons are negative. Fluorine becomes -1, but you just put negative no 1 because we want to be as cool as math and have understood ones. S is 2 columns away from the noble gases, so it's going to steal 2 electrons and become -2. Notice these are written as superscripts. And nitrogen is 3 away, so you guessed it, it becomes -3. So there's a pattern. It goes like this. 1, 2, 3, skip. We're going to skip that one. -3, -2, -1, zip. Because it sounds better. 1, 2, 3, skip, -3, -2, -1, zip. And that tells you what ions they're going to be. Remember, our cations are sweet and positive. Our fire ant ions are mean and negative. An example of an ionic compound is rust, iron oxide. How are we feeling so far? You doing good? Not too fast for you?
Wait, so it's -3, -2, -4, zip.
Over here or here?
Over there
The iron
on the chart.
on the chart, it's 1, 2, 3, skip, -3, -2, -1, zip. Okay, that's our pattern. Okay, you ready to go on? Everybody hanging in there? Keep your hands in the car at all times. Okay, so how do they form ions and make compounds? Lewis structures help with this, so we're going to do lab with it tomorrow. Okay, so cations, you always put first, kitty cats before fire ants. Anions always go second, so we can make a compound. So what you do is you look and you figure out what charge it has. Sodium is in the first column here, so its charge is +1. But we just put plus. Big old plus. We put a plus. Chlorine is 1 away from the noble gases, so it's -1. And 1 minus 1 equals 0. We'll say +1 like that. +1 plus. So we can just put them together. NaCl, that's salt. Sodium chloride. You've heard of that before? Okay. Now here's another one. Calcium is in column 2. So it becomes +2. Fluorine is in the first column over here, so it's -1. Is 2 minus 1 0? No. So that means we're going to need 2 fluorines to balance out that calcium. So we need another fluorine, and then 2 minus 1 is 0. Right? Everybody agree to that mathematically? Okay, so this is how you write it then. That means for every 1 calcium, I need 2 fluorines. There's my 1 and 2. But that's the math behind it, but you really don't have to know the math. All you have to know is you take the charge, and the charge that's the superscript for calcium, you write as the subscript for fluorine. The charge that's the superscript for fluorine, you write as the subscript for calcium. And we're going to practice this with a lab tomorrow or Wednesday where we're going to roll dice and practice doing this. But what you do is you just cross them. I say crisscross applesauce. You cross them, and whatever the charge of one is, you put as the subscript as the other one. Do we feel okay about that? Okay, it'll be better when you practice it. Okay, so then we learned how to write the formula. Well, what about the name? The place that controls the name is called the International Union of Pure and Applied Chemistry, IUPAC. And we're going to do binary names. What does binary mean? How many? 2, right? So we are going to name things that are only 2 chemicals because this is physical science. In chemistry, we can name ones with more, but physical science, it says in our standard, we just do binary. So how you name it is you say the name of the cation, then you say the name of the anion, but you change the ending of the anion to IDE. For example, this one. What is the name of Al? Aluminum. So its first name is aluminum. Okay, and what is the name of Br? Bromine, but we're going to change it to bromide. So it's aluminum bromide. What is the name of Na? Sodium. What's the name of Cl? Chlorine, but we're going to change the ending to IDE, so it's sodium chloride. You get it? Sodium chloride. When ionic compounds form, they are arranged in crystal lattices. So they're crystals, hard little crystals. Ionic compounds have certain characteristics we're going to learn in lab. They'll be on the test. But I'm not going to tell you because I don't want to spoil the lab. We'll do the labbing. You can come back and write it down. Now, why do we have a little Caesar's dude here? It's because there are some names that are more complicated. There's something called polyatomic ions, and some of them have Latin and Greek names. So, like cupric, or you'll hear stannous fluoride on your toothpaste. That's its ancient name. Okay. Now, what about covalent? That's what, remember, ionic was between a metal and a nonmetal. Covalent are between 2 nonmetals. 2 nonmetals. They share an electron pair. They share 2 electrons, and that makes a bond. For example, water, oxygen gas, carbon dioxide, carbon monoxide. We're going to find out the properties of covalent compounds in a lab. I don't want to tell you today. You'll have to find out later in the lab.
Hold on.
Oops. Nonmetals pair. A shared electron pair makes a bond.
Thank you.
Okay. Part 2. So that was our bonds. Now we're to chemical reactions. Okay.
Which is what we are doing the cookies over?
That's what we're doing the cookies over, yes. The chemical reactions. Okay. So a chemical reaction is a chemical change. Remember, triangle means change. One or more substances being changed into something new. The original substance is called the reactants. The new substance is the products. The new substance is the products. Now, evidence of a chemical reaction. For a chemical reaction, you have to make a new substance. Otherwise, it's just a physical change. It's the same substance. For example, if I have liquid water, it's H2O. If I freeze it into ice, it's still H2O. That's a physical change, not a chemical change. Yes?
May I get up and go get a paper so I can get that?
Yes. All right. So I'm going to do a chemical reaction for you. You can buy this little box of chemical reactions at the grocery store, and I did. And I want you to notice what evidence we have that I'm doing a chemical reaction. Okay? Y'all see my chemical reaction is? Okay? I've got two chemicals. See the green right here and the red right there? Those are two chemicals that I'm going to make react. And you tell me what you see that's evidence that something is happening. Okay, what do you see?
Flame.
So fire, yep. So we have, tell me what the fire is. It's two things. If I turned off the light, you'd see better. What is it?
Oh, light.
Light and heat, right? What else do you see?
Smoke.
Smoke. And you might can smell it too, especially you in the front. Can you smell it? You see a little black smoke right there? What else do we have? Notice here. What happened to that end right there? It turned black. So we had a color change, right? Okay. Let's try again. There's another one I want you to get. Everybody be real quiet.
Fire.
A sizzle.
The sizzle. There's noise associated too. Okay, I think I got them all. Let's write them down. So this is evidence that a chemical reaction may have happened. So we could have a change in heat. We can have light. We can have noise. We could have color change. We had the production of gas, smoke, and smell. The one we didn't have is you can also have production of a solid. We're going to do that in lab. We're going to mix two liquids together, and it's going to make a powder, a solid. So those are evidence that chemical change could happen. Now, let's talk about this. I have found in my teaching here at East Paulding High School that there are a bunch of you who have never lit a match before. So all of you are going to do this lab. You're going to strike a match before you get out of here. Some of you have struck lots of matches, but some of you have never done this before. I had some students first period come up to me and say, I've never struck a match. So now's the time. It is life skills. One day you're going to need to light candles on a birthday cake, and you'll be ready. You'll learn in chemistry class. Okay, so chemical reactions can do two things. They can release or absorb energy, heat. So a lot of reactions get hot, but some get cold. Have you ever noticed that?
Can you go back up a little bit?
What? Go back up some? Okay, if it's cold, have you ever had an ice pack where you break something, you shake it, and then put it on? That's a chemical reaction that gets cold, and it's called endothermic. Okay, so it takes in energy, and it feels cold. An example is cold packs. Now, I know this will be shocking to some of y'all, but I used to be a very good baseball coach. I know, it's shocking. I started off just as like the team mom, but I worked my way up to assistant coach in charge of batting. I was a batting coach. And I'm not very good at batting, but I'm very good at coaching it. If you're batting, I can tell you what you're doing wrong and how to fix it. So I became batting coach. But part of my responsibilities as batting coach was I was in charge of the first aid kit. And my boys were that I coached were middle school and high school age, and they got hurt all the time. Y'all might not realize this, but middle school boys are awkward. They fall, they run into things, they hit themselves with the bat, they hit each other with a ball on accident. They're very awkward. So we would go through 2 or 3 cold packs each practice and game. So you would, you pop the little thing, shake it, and I was so good at passing out those cold packs. Well, each of those cold packs is called an endothermic reaction. See how it sounds sort of like it's going in, endo, and thermic means heat. So if endothermic is it takes in heat, energy or heat, what do you think exothermic means?
Gives out.
It gives off. And exo sounds like exit, doesn't? The heat is exiting. So it gives off energy. I already messed that up. Goop. Goop. More fun with sound effects. It gives off energy. Okay? And an example would be hot hands. You ever done, it's the same thing. So sometimes you break it and shake it and it gets hot. They sell those like at the, like at racetrack in the wintertime up by the cashier register.
Oh, I know what you're talking about. I love those.
Those are great. They just don't last long enough. Fun exothermic facts is these reactions are more stable once the bond forms, the chemicals are, and the stronger the bond, the more energy released. Okay? And the great majority of reactions are exothermic. Okay, can I go up to there? Okay, and atoms cannot be created or destroyed in a chemical reaction, so it must obey the law of mass and energy. Matter and energy cannot be created or destroyed, they can only change forms. Now, another thing about chemical reactions I can illustrate here. The chemical reaction here is between green and red. Red is one chemical, green is another. Will they react if I have them here?
No.
Will they react if I do this?
No.
No. For them to react, I have to smush them together. They have to collide hard, and then they're going to react. Then they're going to make a chemical reaction. So that has a name. Okay? It's called collision theory, and it's the particles must collide for a chemical reaction to occur. For example, the match, you had to squish them together. Can I scroll up?
No.
Not yet. Okay. We're doing good. We're about halfway. Okay, can I go now to there maybe? Okay, so how are reactions written? And this is what you're going to do for your cookie lab. So reactions can be thought of like a recipe, and cooking is a form of chemistry. We know that because you can't get the eggs back. You can't get the butter back in your cookies, can you? They only go one way. So this is a recipe for peanut butter cookies that my neighbor, Mabel Johnson, made up. Now, Mabel Johnson won the Pillsbury Bake Off. She won a new kitchen and I think $20,000. New cabinets, everything. This is not the recipe that she won with. There's like a little bug there. This is not the recipe she won with. This is a different recipe. She entered a different year and was like runner-up. Yes?
Is that the back of this? Because I don't have a back.
Go look in the pile. Go find your back. If you don't have a back, go look for it. Because you need this page. Okay? So this is her recipe. A cup of peanut butter plus a cup of sugar plus 1 egg plus a teaspoon of vanilla makes a batch of peanut butter cookies. So this is how you write a chemical reaction. You write the amounts in front, then you write what you're adding, and then you write an arrow and write what you made. So for your cookie lab, you're going to write your recipe like this, like a chemical reaction. Okay, does that make sense to you? So, and atoms and masses are conserved in a chemical reaction. That means what you put in is what you get out. Now, so because of that, reactions have to be balanced. Anybody ever balanced a chemical equation before? Everybody took chemistry? No? Okay, if you have, what it means is you have to have the same number of atoms on both sides of that arrow. So here, this is a recipe, a reaction for making water. Hydrogen gas plus oxygen gas makes water. But if you look, I have 2 black circles on each side, that's good. But I have 2 white circles on this side and only 1 white circle on that side. So this is violating the law of conservation because I don't have the same number on both sides of the arrow. So to fix it, I have to have 2 waters over here. That gives me 2 white circles. But then now I have 4 black circles over here, so I had to go back and add 2 more over here. Now we're going to practice this, but I'll show you how it works. Okay, so this is the rules for balancing chemical equations. You're not allowed to change the subscripts. Where's my little thing here? There you go. Because that would change the chemical. If you have H2O and you decide you need more O's and you put a 2 right there, it's not water anymore. Now it's hydrogen peroxide, and if you drink it, it will kill you. Now, if you drink the hydrogen peroxide at the drugstore, you'll be okay. It's only 3%. But 30%, if you put it on your hair, it strips it white. 100%, you are so dead. You'd be dead at drinking the 30%. But the 3%, people sometimes use it to actually swish out their mouth. If they have an ulcer, you ever had a mouth ulcer or a lye bump? Sometimes it can actually be okay if it's just a tiny bit. There's a lot of stuff like that, though. The tiny bit's okay, but a lot will kill you. All right. Okay, so you cannot change, you do change the numbers in front when you balance an equation, and you never insert a number in the middle of the formula between the elements of the same molecule. Okay, so let's balance an equation. Let's learn how to do something new. Over here I have 1 silver. Over here I have 2. Do you see the little 2? So I'm going to go put a big 2 right there, and now I have 2 silvers on both sides. Over here I have 2 hydrogens. Over here I have 2 hydrogens, so the hydrogens are okay. Over here I have 1 sulfur. Over there I have 1 sulfur. That's balanced. Okay, you think you can do it? Let's try another one.
Can we write that it's balanced?
That's balanced. That's now balanced. Woohoo! Okay. Now let's try this one. 2 hydrogens, 2 hydrogens. Hydrogens are good. 1 oxygen, 2 oxygens. We need more oxygens, so I'm going to put a big 2 right there. But that messed up my hydrogens. Now I have 2 times 2 is 4 hydrogens over there, only 2 here. I need a big 2 right there to make it balanced. Let's do another one. 1 sodium, 1 sodium. 2 chlorines, 1 chlorine. I need a big 2 there. That messed up my sodiums. Come back over here, put a big 2 there. Here's another one. 6 carbons, 1 carbon. I'm going to put a 6 here. 12 hydrogens, 2 hydrogens. I need a 6 there. Now, how many oxygens do I have over here? 6 times 2 is 12, plus 6 is 18. Here I have oxygens in 2 places. I don't want to mess with those because that will mess up everything I did. I'm just going to mess with these. What do you add to 6 to get 18? 12. And what do you multiply by 2 to get 12? 6. Oops. Come on, go slow. So now that is balanced. Let's make this bigger. Now, I've had students go, Ms. Blackburn, it's evil. It's 666, but it's not. Remember, there's an understood 1 here. It's 1666, which is totally fine. Plus, this is the reaction that you're doing right now if you ate any sugar for lunch. That sugar, you're breathing in oxygen, you're breathing out carbon dioxide and water vapor that you are burning up the sugar you just ate. You don't have a little fire in you, but you're doing that reaction.
So not balanced.
It's balanced now, yep. Let's do this one. 2 nitrogens, 1 nitrogen. But wait, well, I could do it. So we're going to put a 2 there. 2 times 3 is 6 hydrogens. What do I need to multiply by 2 to get 6? 3. So now that one's balanced. They get easier the more you practice, and we'll practice them, and we'll do a lab. Okay? Now, what information is in the equations? If you have a recipe, usually it lists the ingredients and there's a little paragraph telling you what to do, right? They put the information, the paragraph, in the equation in chemistry. So equations are instructions. One thing they can tell you about is the heat. Do you see that number 572 kilojoules? That's the heat. It's showing that heat is produced and it's exothermic. Here, heat is an ingredient. That means it feels cold. It's endothermic. Sometimes endothermic is indicated as a positive number and exothermic as negative. So that's just a little something there. Okay, all right, moving on. Reactions and equations. Sometimes reactions indicate the state of matter. Do you need a solid, liquid, or gas? Okay, so here's an example. Here's my match reaction I did, and they were solids, weren't they? The green and the red were solids, and what it actually produced with the match, not burning the wood, but the match was also solid. So, see that little S in parentheses? That doesn't mean sulfur. That means it's a solid. If there's a little L, it's a liquid. G, gas. AQ means aqueous. It's in water. If it's got degrees Celsius, it's a temperature, and they write it over the arrow. So when you write your cookie recipe, peanut butter, whatever, write the temperature you cook it at above the arrow, and write the time, how long you cook it below the arrow, okay? CR means it's a crystal, and arrow down means it makes a solid, arrow up a gas, arrow over, that is yields. Sometimes it has a chemical line over the arrow, that's a catalyst. It's something that doesn't take place in the reaction, but it helps it. Y'all learned about catalysts last year in biology. Remember how you learned enzymes or catalysts in your body that help reactions happen but don't take place in the reaction? Do you remember that biology? Okay, arrow two ways means it's an equilibrium or that it's a reversible reaction. You're used to those because you're used to recharging your phone. It's a reversible reaction. A triangle means you heat it up. Sometimes it has the word heat to mean you heat it up. KPA means you have to put it under pressure. You're used to that. Some of you have Instant Pots and you do your cooking under pressure. You're used to that. A little E means electrons, and it means you shock it, just like Frankenstein. Sometimes you have to shock your reaction to make it work. Okay, so these numbers in front are called the coefficients, and they can tell you about the moles, the molecules, the mass, or the total mass. And if you take chemistry, then you'll learn how to tell all of those, but we don't care about that in this class. Okay, so how can reactions be used? Why would you want a reaction? Why would you want the reaction for cookies? What do you want when you do that reaction? What do you want to get out of it? Cookies, right? So you can want the products, like the cookies. What about my match reaction? Did I want burnt matches? Is that why I paid money for this? No, what did I want from this reaction? I wanted the fire. I wanted energy. So that's why you might want a reaction. Why would you not want a reaction? So like that poison right there, do you want that? No. So sometimes you don't want the products. What about a bomb? Do you want the explosion? No. So sometimes you don't want the energy. So reactions, is why you do them is why you don't want them. Now there are 5 types of reactions. Okay, and they're easy to remember if you just think about love and romance. Everybody feeling romantic? Okay, so you can have a couple get together. Oh, these two were lonely, but now they're together. So that's called, so compounds are made in a synthesis reaction. I had lonely hydrogen and lonely oxygen, but now they're happy water. Okay, so that now, if you can have love, what else can you have? Hate, or the couple can do what? Break up. So, draw your broken heart. Broken heart. Compounds, let me get on my right page here. Okay. Okay. Compounds are broken down in decomposition reactions. So here we have the happy couple, they broke up. So here we have a chemical that broke into other things. Now sometimes it's not that simple. Sometimes there's a little scandal involved, maybe some gossip. What happens then? The affair, right? Okay? Well, chemicals do this too. Okay, so the affair is called single replacement. Single replacement. Here we have this happy couple. And see this guy? He cut in. And look, she ran off with him. And poor guy all by
Why
himself.
is science so sad?
He's so sad. So look over here. Here's the happy hydrochloric acid. But then there's zinc. And zinc is good looking. He's got money. And what do you know? Boom. Chlorine runs off of zinc. And poor hydrogen has to go off all by himself. He got replaced. Single replacement. Now, it's hard to look at zinc and know if he's good looking or not. Because, there are affair proof of relationships. How do we know if it's true love or not? Well, you look it up in the chart. It's called an activity series, and it predicts if a reaction will happen or not. You can think of it as a strength ranking list, the strongest element on top and the weakest on bottom. So, zinc is stronger than hydrogen, so zinc is able to replace hydrogen. Okay? So now, sometimes it's not just the simple affair. Sometimes you got the affair, right? But there's two people who got wronged. And they say, let's go to Starbucks and talk about those no good, low down, dirty dogs. Sounds good. So they're at Starbucks and they're talking about how terrible their exes are. And suddenly, love starts to bloom at Starbucks, right? So sometimes what happens is the do-si-do. The double replacement. I had a student once and she said that is exactly what happened in her family. Her dad cheated with who became her stepmom, and who became her stepdad would go with her mom, and they would go to Starbucks and talk about how terrible they were, and then they fell in love and got married. And my student said it was the best thing ever, that she liked her stepdad so much better than her real dad, and that everything worked out perfect for her. She got rid of the bad dad and got a good new dad. So she was like all for double replacement for her family. She said it was way better. So here we got it. Silver is with nitrate. Potassium is with sulfate. Do-si-do, silver goes with SO4, KNO3, potassium nitrate. Here's that one couple, here's another one. They do-si-do. It happened in like the 70s. Do y'all know in Robin Hood, do-do-do-do-do-do-do-do. You know how there's all those songs in Robin Hood? The guy who sang those, he switched wives with a guy named Glenn Campbell. They were both big stars at the time, and they did the do-si-do. They ended up with each other's wife at the end. Okay, now when this happens, the cation swaps for the cation, they're written first. The anion for the anion is written second. Our last kind of reaction is burning, combustion, adding oxygen. Complete combustion of a hydrocarbon looks like this. That's methane. This is the gas that's in our outlets. It's in your house if you have a gas stove. It's the kind of gas you pooped when you pooped. And yes, they're flammable, but don't try to light them. You can get burned on your bottom. Okay, so methane plus oxygen is burning. It makes carbon dioxide, water, and energy. This is called complete combustion. But some combustion is incomplete. Like my match. And it produces carbon monoxide, smoke, and ash. And this is dangerous. Carbon monoxide can kill you. So always be careful about having fires in a non-ventilated space. You can die. It's why car exhaust can kill you. You ever heard of anybody dying in a garage from car exhaust? Yep, that happens. All right, last idea, solutions. So what is a solution? A solution is a mixture that has the same composition, color, density, and taste throughout. It's clear but not necessarily colorless. Kool-Aid is our example. What does homo mean? Same or different? Same. So a homogeneous solution is the same throughout, like Kool-Aid. If it's hetero, what does hetero mean? Different, and it will have layers. It's not the same. So like Italian salad dressing is heterogeneous, homogeneous, or homogeneous is milk. Milk is the same throughout if it's homogenized milk. The solute is what gets dissolved, like the Kool-Aid powder. The solvent is what does the dissolving, like the water. How does this happen? It's all because opposites attract. So here are these ions. That went way too far. Here are these ions that get attacked by the water. That's why I said Mickey Mouse attacks. I think that looks like Mickey Mouse. But I've had students say, nope, it's unimpressed Kermit the Frog. But whatever it is, the water attacks because of opposites attack, and it pulls it apart. It disassociates. Now then, what can be dissolved? Solid, if you may have sweet tea, you can have the sugar solid dissolve in liquid.
What?
If you have sweet tea or Kool-Aid, something like that, solid can dissolve in liquid. Also, if you have soda pop, Coca-Cola, you can have gas dissolve in liquid. That's what the bubbles are. You can also have metal dissolve in metal if you melt them, and that's what like brass is, a lot of jewelry and stuff like that. Now, let's talk about dissolving a solid in a liquid. So you go up north and you ask for sweet tea, and they look at you like you're crazy, and they bring you a glass of iced, unsweet tea and a packet of sugar. Is that sugar going to dissolve? No, but what are you going to try? You open it up, you pour it in, and what do? You stir it. So one thing that can help is stirring. But if you really want that sugar in the tea, when do you have to add it? While the tea is what? Hot. So you need heat, also helps things dissolve. Okay? And then the last thing, have y'all ever bought those little packs of Kool-Aid? They're like, look like a little finger. It's got real sugar in it, but if you pour it in water, it will dissolve in cold water. Anybody ever bought those Kool-Aid singles? Why does that dissolve, but the little pack of sugar won't?
A different type of sugar?
It's that the particles are smaller. They've ground up the sugar so small it will dissolve. So that is particle size. Yes, India? You want to get some water? Sure. Particle size. So here are three things: stirring, heat, and particle size can speed it up. Now, how much can dissolve? Here are some words, some vocabulary words. Solubility is how much can dissolve at a given temperature. Concentration is how much is dissolved. The symbol for it is square brackets. If something is saturated, no more can dissolve at that temperature. If it's unsaturated, more can dissolve. And there's a thing called supersaturated, where you trick it into more dissolving at a temperature than can by heating it up, dissolving a bunch, and real carefully cooling it down. Do you have a question, Brian?
I'm using pressure.
You don't have any passes left. We'll discuss it. You only got 10 minutes.
Oh, wait.
I need to go
That's
back.
not gold.
No, you may not. We're doing notes. Guys, we got 10 minutes and we're finishing these notes. Be quiet. 10 minutes, we can do it. You can tell how much dissolves using a graph called a solubility curve. We'll be doing an activity with that. Now, what improves dissolving gas in a liquid? So, soda pop. What helps it stay fizzy? For it to be hot or cold? Cold. And also, once you open it, you hear psh, and it's not under pressure anymore. Pressure helps it stay dissolved. So it's a little different. Now, particles in solution. When you have ions in solution, they become charged. Charged ions in solution and can conduct electricity, and they're called an electrolyte. Gatorade is an electrolyte. Have you ever noticed it has a lightning bolt on it? It's because Gatorade conducts electricity. Now, what happens when you have solute particles in solution? It will lower the freezing point. That's why they put salt on roads. And it raises the boiling point. So when you put salt in the water for pasta, it boils at a higher temperature. Now, not everything dissolves. So what's the rule? Like dissolves like. That means that if something is polar and has charged ends on one side, like water, it can dissolve water-based things. Non-polar things that don't have charged ends, like oil, dissolve things that are more like permanent markers. Does water and oil mix? No. But soap is both, so if you put soap, it'll mix together. Now, last idea here, acids and bases. Which one, acid or base, tastes sour? Which one tastes sour, an acid or a base? An acid. So acids taste sour, they have hydrogen ions, they react with metals, they turn blue litmus red, they have a pH of 0 to 6.9, and an example is a lemon. A lemon is acidic. The opposite is a base. Bases taste bitter. You can remember that because base and bitter start with B. They have OH hydroxide ions. They feel slippery. They react with fats. They turn red litmus blue. They have a pH above 7. And an example is soap. Soap is normally basic. Okay, so we're going to do a lab with that. Now, they can be strong or weak. Strong acids dissociate completely, as do strong bases. And they're more dangerous, they're stronger, and so that's why some things like hydrochloric is worse than, say, citric acid. How do you tell about an acid or a base? With an indicator. We're going to do a lab with that. If you mix an acid and a base, you get neutralization, and you get a salt and water. And that's why we got salt water drawn right there. All right, is that it?
Can you go back up?
Oh, I forgot one.
Mushroom.
Hold on 1 second. Good. Okay, and this is water. Water is neutral. It has no taste. It is a pH of 7, water, and it's got H and OH. And that is the notes. Yay, we did it. Like, share, subscribe. Science is great.